Okay, so the last lecture of the semester, and as promised, we're going to review for the final exam, which is coming up, but let's go to the board. Let's talk about what's happening the rest of this week. You do have a chance to turn in your last homework assignment. It's due Thursday midnight, November 30th. So Thursday midnight on Canvas. Make sure you turn in your fourth homework assignment. I will be posting the top 5 quiz scores for everybody later this week, because we're finished with quizzes now. That'll be posted, so take a look on Canvas for that. And then, of course, your final exam, Saturday, December 2nd, 5:30 to 7:30 p.m. I'm going to go to that here in a second and talk about which particular classrooms we're using. But before I do that, I just want to remind you, I know you should be getting notices via USF that the evaluations for this course are online. So please fill those out. I use those to help me do better next time around. Okay, so final exam. Let's take a look at the smartboard here. All right, so pretty much everybody's going to Business 1100 except for 2 sections. Okay, if you're in the Wednesday night class, you're going to go to Business 1201. If you're in the Tuesday, Thursday 330 section, you'll go to Business 1301. That's right around the corner from Business 1100. Everybody else, all the other sections, Monday, Wednesday 8, 330, Tuesday, Thursday 9:30, Tuesday, Thursday 2. You're going to go to Business 1100, and of course, if there's any overflow, just go into Business 1100. So if you're not sure, go to BSN 1100. On Saturday, December 2nd. Remember, the test is from 5:30 to 7:30 p.m. We'll start right at 5:30. You'll have the full 2 hours to take it. Try to minimize how many backpacks you're bringing in and carry bags. Of course, no calculators permitted. You won't need them. And cell phones will need to be turned off. And then I'll post final exam scores and final grades no later than Monday, December 11th. Okay, so that's the final exam. Okay, please make sure you come to this test. It's the only final exam time that is USF made available for this course. There are no other times during finals week. This is it. You miss it, you'll get a 0 on the test, so I don't want that to happen. All right, so that's the final exam. Now, as far as reviewing for this final, before I do that, I want to review last lecture, just real briefly, because we did talk about some new material last lecture. So let's take a quick look at last lecture. All right, so we're talking about time series forecasting. We finished that up. And we tried to emphasize the fact that there are some smoothing methods that are very easy to use because they only rely on past values of y. So I'll put it here also, past y values, only past values of y. Makes it easy. They smooth things out. The problem is there's no test to allow you to determine whether the model really is going to do a good job. You kind of have to wait until you make the forecast and see the result. Then we talked about least squares regression, where we know there are tests available. Tests of model adequacy, model statistics like R-squared and R-squared adjusted, standard deviation, all kinds of things that help you evaluate whether or not the model is going to be useful, as well as confidence intervals. So we talked about that. Then we talked about the fact that in a least squares regression, one of the drawbacks is that you have to assume that the error term is normally, you do have to assume it's normally distributed, but you also have to assume that the error term is independent, and it's very likely with time series data, right, because we're talking about the experimental unit being a unit of time, it's very likely that with time series data you can have correlated errors. That's called autocorrelation, okay, AC, or autocorrelation, correlated errors. And so there's a test available to determine whether or not your errors are correlated. The null hypothesis is that the errors are independent. The alternative is that the errors are correlated, and mostly positively correlated. So if you end up rejecting this null hypothesis in favor of HA, well, that's going to be a situation where the errors are correlated, and you really shouldn't be using the least squares regression model. That's going to lead to some problems. So what you need to do is to model that correlated error. And that's how we finished up the lecture. Whoops, skipped page. That's how we finished up the lecture by talking about what is called a time series error model, where there's 2 models in one. Okay, here's the initial model, okay, and it looks just like any regression model. You've got the mean component, the mean of y component on the right-hand side, and then you have an error component on the right-hand side. I'll call it R for residual. But you model both. You model the mean component, that's just like normal, okay, so time might be in there as a variable, as an independent variable. Cyclical variation could be in there. Squared terms could be in there. Dummy variables can be in there, maybe for seasonality. Interactions. So just like normal, nothing new with respect to that piece. What's new is the correlated error piece, so you have to actually model the correlated error. Here we're showing that the error at time t, residual at time t, is a function of the residual at the previous time period, t minus 1. You put the two together and you make up the time series model. So that's how we finished the class, by talking about that. Okay, now let's talk about reviewing for the final. Okay, first thing is, remember that this final exam is going to be cumulative from the point where we started with new material. Now, that doesn't mean stuff from Stat 1. That means starting with analysis of variance. So let's look at the different topics we talked about. Okay, so ANOVA came out of Chapter 9, analysis of variance. That's where you want to compare means. All right, categorical data analysis coming out of Chapter 10. Of course, categorical data means qualitative variables. So we're testing proportions associated with qualitative variables. Then, of course, we spent a lot of time on regression analysis. That comes out of Chapters 11 and 12, a simple linear regression in Chapter 11, multiple regression in Chapter 12. So a lot of stuff there. There we're modeling a dependent variable as a function of independent variables. And then finally, we finished up with the time series forecasting, which is coming out of Chapter 14. I know I get a lot of questions from students saying, I can't find Chapter 14 in the book. That's because it's not in the book. It's on the PDF that I posted to Canvas. That's where you're going to find the problems for Chapter 14. Anyway, that's predicting a value of y for a future time period, okay, with time series data. So those are the 4 different groupings or topics that we talked about. Now let's take each one and just a way to try to help you identify when you need to run an ANOVA, when you need to run a categorical data analysis, when you need to run a regression, when you need to look at a time series forecasting model. So let's take a look at them one at a time. Okay? So start it with comparing means using an ANOVA. So the key words here are means. And the type of data you're going to be looking at is quantitative. So your dependent variable y is quantitative in nature. And then you're looking at the mean for that variable. Now you do have a qualitative variable which represents the treatments, okay, the groups that you want to compare. These are the treatments or the populations or the groups that you want to compare the means on. And remember, your null hypothesis is that the means are the same, and that's going to be an F-test to determine whether the means are the same. So I've got mu1, mu2, mu3. Could have more than that, of course. And then if you decide that you reject HO and you decide the means are different, right? If you decide the means are different, then what's logical to do? Well, follow it up with a ranking of the means using Tukey's method. Okay, so that in a nutshell is what we want to do in an ANOVA. Of course, there are some assumptions. You have to assume that the dVy is normally distributed for each of the treatments, and you also have to assume that the variances are equal. So there are some assumptions to look at, but these are just some things to help you identify when you're dealing with an analysis of variance. It's kind of easy if you think of it this way. You're dealing with quantitative data and a mean on that variable, that quantitative variable, and there's more than one mean. Means from different populations, different groups, different treatments, whatever you want to call them. And you simply want to compare them. So keywords being means, comparing means. Okay? So that's ANOVA. So we talked about that. That came out of, remember, that comes out of Chapter 9. All right? Then we talked about some material that comes out of Chapter 10, where we were testing qualitative variables or categorical data, qualitative variables. And of course, when you're dealing with qualitative variables, no longer are you dealing with means, you're now dealing with proportions. And there are tests of hypothesis that you want to conduct, and these aren't F-tests. They're instead called chi-square tests because the test statistic is different. Of course, the p-value, you're always going to remember this, okay? So in any test of hypothesis, you pick alpha, you compare it to the p-value. And if alpha is greater than p, you're going to reject the null hypothesis. That's just a given. To remember that for any of these tests. Anyway, these are chi-square tests, and there was 2 different tests. It depended on how many different qualitative variables you were examining, you were studying. If there was just a single qualitative variable, then you're just looking at a comparison of the proportions associated with the different levels of that qualitative variable, right? The outcomes for that qualitative variable. Could be 2 or more outcomes. So you simply compare the proportions associated with those, and your null hypothesis would be that those proportions would be the same. All right, when you're dealing with 2 qualitative variables, then what you want to know is whether those 2 qualitative variables are independent or not. And the null hypothesis there would be that they are independent. And of course, you'd have printouts associated with each of these, and you again pick your alpha, find the p-value, make the comparison, and then decide what's the case, what the result is. And there is an assumption you need for this kind of data also, and this is simply you need a large sample. And that is going to happen when you have expected numbers in the different cells of the table greater than or equal to 5. So we talked about that. So those are the two things that come from, prior to regression that you're responsible for on the final exam, because they're really considered new material. All right, then we got into regression. So that's the third topic. Of course, this comes out of chapters 11 and 12. And there's so much stuff here I couldn't possibly write it all down. Okay, but the general idea is this: you've got a dependent variable of interest. It needs to be quantitative in nature. So you're talking about a quantitative dependent variable, and you want to predict its value or model it. So prediction, modeling might be the key words. Predict, model might be keywords to help you identify that you're in dealing with a regression analysis. And then there, of course, are independent variables. These are x's. And of course, just like on your project, they could be quantitative or qualitative. So you could have a mix of variables, quantitative or qualitative. We looked at various models. Think your project, okay, and that'll help you. We looked at a first order model, a main effects model, a curvature model that had a curvature, a model that had interaction. Okay, so we looked at different kinds of models depending on the kind of variable we had, quantitative or qualitative. There were several tests of hypothesis that were important. Okay, there was a global F test to test the entire model, all the betas except beta naught simultaneously equal to 0. There was a t-test on a single beta, if you wanted to test just one beta. There was a partial or subset F test on a partial set of betas, not all but more than one. Okay, so we talked about that. Of course, I didn't write here, I'll write them down now. There are also statistics we looked at, like R squared and R squared adjusted, and twice the standard deviation. Okay, so we looked at a number of different tests, not test statistics, but statistics that help us evaluate model adequacy. So there are a lot of things that went into that. We discussed the idea of multicollinearity, MC, where your x's are correlated and how that could be an issue. We also talked about a residual analysis where you plot residuals to help you check assumptions. All right, we talked about all that. And of course, remember the assumptions. I used a little shorthand notation there, but 0 means zero mean. Errors have a zero mean. Sigma squared means constant variance. Errors have a constant variance. N means errors are normally distributed. And then one of the I's means errors are independent. So there's your four assumptions: independent, normally distributed, mean is 0, constant variance, and of course the residuals help us check those assumptions. So we spent a lot of time on regression. And then finally we finished up with time series forecasting. Of course that comes out of chapter 14. And again, dealing with time series data. I've been trying to harp on it all semester. We started way back when our first application of a regression problem, the least squares, the simple linear regression, where we were modeling the stock's rate of return in a year. Our experimental unit there was a year. That was our first exposure to time series data. And we've covered it a lot. Yet I'm going to tell you, it's one of the most missed questions on the final exam by students. There's confusion there. I'm not sure why, but just think of it like this. To know whether you have time series data, it's your experimental unit. It's the object upon which you take a measurement that has to be a unit of time. And then you measure a variable on that in that particular time period. So here we're trying to model YT for forecasting purposes. Of course, forecasting means predict the future. So predicting Y for a future time period. That's what we want to do. And of course, there's several models. We kind of already went over them. There's some smoothing methods. And they're actually just listing assumptions there. There's really no assumptions you need for those smoothing methods, which is why they're very popular. But they have drawbacks, okay? No test of hypothesis, limited to short-term forecasting, that kind of thing. Then we talk about least squares regression, and of course there's assumptions there, and one of the assumptions is the errors are independent, and that might not be true, and the Durbin-Watson test would tell us if that was true or not, and likely not to be true. And then if it's not true, you're better off fitting a time series error model where you actually model the correlated errors. So in a nutshell, that's the different topics that you're responsible for the final exam. Now, before I go, a lot of students want me to do the practice final. Of course, I know that, and I'm going to do that. Okay, but just a few study tips. Okay, I mean, what you can't do, and what I don't want you to do, because it just doesn't generally work out, is just study the answers that I'm going to give you now on the practice final that's in the class notes. I mean, if that's all you do, you shouldn't expect a very good grade on this final. Okay, I will tell you on the final there's going to be 33 multiple choice questions. One of them will be a free question, where you'll see when we do the practice final. One of them will be a free one. So there's really 32 to answer to get points on. And you may think like, well, it's a multiple choice test, so look, I'm going to see the right answer. It's going to be on there. It's going to be obvious to me that I know what it is. Not usually true. Simply because there's also going to be 4 wrong answers listed. And those 4 wrong answers are going to sound good. Why am I telling you they're going to sound good? Because I get them from students who write them. All right, you're writing out answers on these other tests, right? And we grade it. And so we see how people write out their answers, and so, oh, they must think that's right. Let's put it down. Let's, maybe somebody will select it. So that's what, in my mind, it makes the test harder. So you really have to know your stuff to do well in the final. Anyway, study tips. Go back to your old exams. If you haven't picked up your old test yet, you're running out of time. Stat Lab's going to close this week on Thursday. That's the last day it's open. You need to go back and pick up your old tests and look at what you missed so you can figure out how you can do better. So make sure you know what you did wrong on the previous exams. That's certainly number 1 on the list, I would think. And of course, I've tried to emphasize all semester practical interpretations, because in the real world, that's the kind of thing you're going to have to do. And how can you practice on those? Look at the class notes. And in the class notes, anytime something is in bold type, bold print, it's a practical interpretation. And so you can just go over it over and over again with the different practical interpretations and hopefully study those. And then finally, now I'm going to go over the practice final that's in the class notes. Obviously, you can go over that too again. But there's also another one that's posted on Canvas. Okay, and I'm not going over that one. The answers are posted there also, but in a separate file. But that's the one I would kind of leave till last. Okay, and say, okay, I've done my studying. I think I'm ready. I'm going to give myself 2 hours. And by the way, you won't need 2 hours to finish this test. You have it if you want it, if you need it. But you more than likely won't. Probably after about an hour, you'll be done. Anyway, give yourself some time. Close your notes. Close your books. Take that practice final that's posted on Canvas. Answer the questions. When you're done, go compare them to the answers that are posted. If you do well, you're ready. You're ready. If you don't do well, hey, you go back and try to shore up the areas where you did. So anyway, that's my suggestions. Hopefully you'll follow those. Now, let's take a look at the final exam that is posted on Canvas and also in your class notes. Now, I've highlighted the answers in yellow, and I didn't want to do that, the first time we go through it, but it's just so much easier for you to see what the right answer is. So I'm going to go ahead and do it that way, but I'm going to assume we don't know what it is. And we'll look at why the answer that I've highlighted in yellow is the correct answer. Okay, so practice final exam. And you can see what's going to happen. There's going to be a story, just like you've seen in the past on the exams I've given you. There's going to be a story. And then what I'm going to do is I'm going to tell you which questions that story pertains to. So you can see questions 1 through 16, okay, have to do with this story about a diamond collector who wants to predict the price of diamonds sold on the open market, gets a random sample of 60 diamonds, and measures 3 variables: price, Y, asking price in dollars, size, number of carats, X1, and color, 1 of color D, 0 of color E, that's X2. Look, without even studying a whole lot, it's obvious this is a regression problem. I use the word regression in the story. Okay, it's kind of obvious to know that you're dealing with regression. Maybe some of the other ones won't be so obvious, but this one's pretty obvious. Okay. So first we fit a simple linear model. You can see it there. It's got X in it, X1 in it. That should be an X1 there. X1 being carat, okay? That's all that's in the model right now. And then there's a bunch of printouts that are associated with this analysis. Okay, we'll go look at them in a second. But first question, you already know I'm going to ask you this, right? I've asked it to you on every test. What is the experimental unit for this analysis? What is the experimental unit? Now, to figure that out, if it's not obvious to you, go back up and look at the story, okay? And the second sentence, the collector obtained a random sample of 60 diamonds. There you go. A sample of 60 diamonds. And then we're going to measure a bunch of stuff on each diamond. What we measure, these are not the experimental units. It's the diamond that is an experimental unit. And we're going to measure price, and we're going to measure carat, and we're going to measure color. So it's a diamond. It's a diamond. Number 2, which of the 3 variables measured are qualitative? Hopefully that's easy. Oh, asking price, that's quantitative, that's in dollars. Number of carats, another quantitative variable. And that leaves you with color as the only qualitative variable, so A, color only. Oh, by the way, before I go any much farther, okay, I should have shown you this, my bad, okay? Let me just stop there for a second. I want to move over to the overhead camera, okay? Because you're going to have to fill out a Scantron, okay? and I know you've done this before, but I just want to point out some things because there'll be a lot of people funneling into the final exam, and it's going to be crazy, you know, with all 600 some students coming at the same time. So what you're going to do when you get your Scantron, of course, you're going to bubble in, put in your name up in this section. Down here for identification number, that's your USFID, so make sure you have that. You'll just leave section blank. Don't worry about that. We don't care what section you come from. Okay, leave that blank. And then on the front of your exam that you're going to have is going to be a test form code. It could be any one of these letters. Okay, so you're going to bubble in that. That's really important to make sure you bubble that one in. And then, of course, you'll start answering the questions and bubbling in your answers. Okay, so that's what the Scantron looks like. You can start, you know, as soon as you get into the exam, you can start filling out your name and your USFID and, of course, your test form code. And then you'll sit tight until everybody gets in, and then we'll start you, and then you'll start bubbling in your answers. Okay, so I want to make sure I showed you that. All right, now back to the test. Okay, so we talked about the first two questions. Okay, question number 3. A plot of the actual data for the 60 diamonds is shown in printout number 2. We're going to go look at that here in a second. Note that the points do not fall in a straight line or curve. Is this a problem? Let's take a look at the picture first. There's printout number 2. Okay, notice price, actual price, that's the dependent variable, is plotted against x1, which is caret. Okay, and then the colors are the different dots. Blue is color E, and red square is color D. So there they are. That's not a perfect straight line or curve, is it? No, no, it's not. But does that surprise you? That shouldn't surprise you. We're not dealing with deterministic data here where if you know one variable, you know exactly the value of the other. No, we're dealing with probabilistic data here where there might be a general trend, but there's going to be variation around that trend. And so, no, that's not unexpected at all. So let's see if we can figure out what the right answer is now. Going back up, is this a problem? Well, we read all the answers, obviously. Here, A, no, we do not expect a deterministic relationship between price and size. That's the correct answer. One suggestion I would make to you, okay, on taking this final exam with the multiple choice. Try not to look at the answers initially. Okay? In other words, assume or pretend as if it's open-ended question, like I asked you on the previous 3 tests. And try to write out your answer and then see if your written out answer matches up with one of the 5 that are posted. That's a little bit better way. Now I know if you don't know the answer, you're going to start reading. I get that. But you can get tripped up and confused if you start reading first. Okay, so I would try writing down my answer first and then seeing if it matches up with one of the ones listed there. Okay, so that's answer A. Then you'll get true, there'll be some true false on it also, and so here's a true false. And you might say, well, that's easy. I would tell you this true false right here is probably one of the harder questions on the test. Let's read it. Okay, true or false? At alpha equal to 0.02, there is sufficient evidence of a positive linear relationship between price and size. What are we going to have to look at to do this one? First of all, let's think of it this way. At alpha equal to 0.2, we must be doing a test of hypothesis, right? If we're picking an alpha, we must be using a test. And then if we're going to conduct a test of hypothesis, we're going to have to find the p-value. So we're going to have to go to the right printout and go to the right p-value so we could compare alpha to p. Now, what printout? Well, let's read the rest of it. There is sufficient evidence of a positive linear relationship. Oh, that's regression. That's simple linear regression. That's testing the slope. Positive linear relationship between price and size, because right, size is the only variable in the model right now. So that's simple linear regression testing the slope. So let's go find that printout. All right, so we come cursor down. Printout 2, printout 3. No, that's not it. Printout 4, there's a printout. Regression printout. The only variable in the model, caret. The coefficient 14,380, that's your estimate of the slope. Right above it is your estimate of the y-intercept, negative 3090. But we want to do the test on the slope. So we want to come across to this t-test, and there's the p-value. Now be careful because remember these t-tests here, these p-values are for two-tailed tests, right? Don't forget that, two-tailed tests. That was one of the Jeopardy questions. These p-values are for two-tailed tests. Do we want to do a two-tailed test? Because if we did, we would just take the p-value the way it is. But do we want to do a two-tailed test? Let's go back up and look. Let's make sure. Let's read the question. There is sufficient evidence of a positive linear relationship. Is that a two-tailed test? No. That's one-tailed. One direction. Beta 1 positive. Slope positive. That's one direction. That's a one-tailed test. So we actually need to go back to the two-tailed p-value and divide it in half. Now, it turns out it wouldn't have mattered here, but it very well could matter. And so you really should be using a p-value 0.0015 divided by 2, which is pretty small, 0.007 or something like that. And that's going to be smaller than alpha, because we picked alpha 0.02. That's going to be smaller than alpha. And therefore, we're going to reject HO in favor of HA. And if we do that, we're going to say there's sufficient evidence of a positive linear relationship. And so that makes that true. So there was a lot of work involved to get this answer. A lot of work involved to get the answer, the true false. All right. All right, how about the next true false? Number 5. A practical interpretation of the y-intercept of the line is the price of a diamond will be negative $3,090 when the size is 0 carats. Do I need to even go look at a printout to determine this? You shouldn't have to, right? Size of a carat equal to 0, size of a diamond equal to 0. What kind of diamond has no size, has no carats? It doesn't exist. It's a value of x that's totally nonsensical. Size of 0 being totally nonsensical. Certainly it's outside the range of the sample data at minimum. But it's totally nonsensical. No, that would not be a practical interpretation of the y-intercept at all. There is no practical interpretation. It's not the negative value, although that might alarm you. It's not the negative value of the y-intercept that really alarms you. What should tip you off is the fact that we're setting size equal to 0, and that's totally nonsensical. So that's false. That's false. All right, number 6, true or false. We are 95% confident that the price of a diamond, of a single diamond, let's read the whole thing, that the price of a single diamond with the size of 0.5 carat will fall between $3,700 and $4,480. Well, obviously we're going to have to go look at a printout to see if this is right. But what printout do we look at? So it's obvious, right away in the beginning of this test, and you can see, you've got to know your printouts. You've got to know what they look like. And so practice on those. I should have added that to the study tips, okay? Practice on the printouts. Go look at your class notes. See which printout corresponds to what kind of an analysis and know what it looks like and where to look. All right? All right, so now let's see this. Confidence, this is a confidence interval, obviously. For a single diamond, oh, that's a confidence interval. That's a prediction interval for y. Now, why do I say prediction interval? Because it's for a single diamond, not for all diamonds. And it's not on a mean. It's on the individual price. So here I need to find the prediction interval for y when x, notice size 0.5, when x is 0.5. So let's see if we can find that printout. Not printout 4, but it's printout 5. There we go, printout 5. And remember, the left-hand side is the prediction interval, and the right-hand side is the confidence interval on the mean. So looking on the left-hand side, there's your 1390 to 68. Oh, those weren't the numbers reported in that question. The numbers reported were 3721 and 4484. So the numbers reported were for a confidence interval on the mean of y, not for a prediction interval for y. So that's going to make it false. Now, the carat of 0.5 is right, but we don't have the right interval. So coming back up to our question, true or false, it's going to be false. Now, here's another good way to practice for the final, okay, to get students out of memorizing this particular answer for this particular final. How could you make a true-false question, which is, say, false, true? What could we do to the story, to the question, to make this true? How could we make this true? Well, we're 95% confident that the price of a single diamond with a size of 0.5 carat will fall between, you'd change the numbers, wouldn't you? You'd go get the prediction interval numbers. That's one way to make it true. I know another way to make it true. Keep these numbers, 3721 and 4484, and change the words. What words would I change? Well, it's a confidence interval for the mean. So instead of saying price, it would be mean price. And instead of saying for a single diamond, it would be for all diamonds. See, that would make it true. We are 95% confident that the mean price for all diamonds with a size of 0.5 carat will fall between the $3,700 and the $4,400. That's a good way to practice for this final, okay? Try to change what is true to a false, try to change what is false to a true by changing the words. Okay, all right, so we've looked at these printouts already. There's some more to look at, but we need to go down to the next question and then we'll go look. Okay, number 7. Give a practical interpretation of the model standard deviation S. And number 8, since we're there, give a practical interpretation of the coefficient of determination R squared. And then number 9, give a practical interpretation of the estimated slope. Let's go find all 3 of those numbers first, and then we'll come back and we'll answer this question. Okay, so they're all going to come from the same printout. The simple linear regression printout, this one, number 4. They're all going to come from printout number 4. Okay, R squared, 0.90, let's remember that. Standard deviation, 1342, let's remember that. And the estimated slope, 14,380, let's remember that. Okay, so those are the 3 numbers we have to interpret, right? All right, so number 7, interpretation of S. That's the 1342. Well, you know you have to double it. You've got to take 2s, and you're going to interpret 2s. So 2s gives you 2684. I mean, one way you could kind of take the back door into the right answer is just look for an answer that's got 2684 in it. Now, there could be more than one. Turns out there's only one here. And you look at it. It's answer E. About 95% of the actual diamond prices will fall within $2,684 of their predicted values. And of course, we've interpreted S that way the whole semester, right? Anytime we've interpreted S, it's always about 95% of the actual Y values are going to fall within 2S of their predicted value. So this should be, one you know by heart. So anyway, it makes answer E the right answer. About question 8, interpret R squared. We said that was about 0.90. So obviously 0.90 needs to be in one of your answers, but remember now, it should be interpreted as a percentage. And again, an interpretation we've done many, many times over the course of the semester. R squared represents the proportion of variation or the percentage of variation in Y that can be explained by the model. So the right answer there is about 90% of the sample variation in prices, because that's Y, can be explained by the model. That's answer D, about 90%. And then finally, number 9, the interpretation of the slope. That was the 14,380. Remember, the slope is how much Y changes for every 1 unit increase in X. So you have to increase X by 1 unit. Of course, in this case, it would be size increasing by 1 carat, and see how much price changes. And of course, that's a positive number, so price is going to go up. So it should be, somehow the answer should talk about price increasing. Oh, there it is, answer A. We estimate the price to increase $14,380 for every 1 carat increase in size. Now, a lot of the answers in all 3 of these questions, a lot of the wrong answers look right, and the reason why they look correct is because they're correct answers to a different question. They're correct answers to a different question. For example, look at number 7. Answer D. About 90% of the sample variation in prices can be explained by the simple linear model. Well, that's the wrong answer for number 7, but that's the right answer for number 8. So, got to know your interpretations. Know your interpretations. All right, number 10, give a value of the dependent variable that will lead to an unreliable prediction interval for asking price. Okay, this is where, remember, the independent variable is carats. You've got to give a value of carats size that is outside the range of the sample data, but you got to know the range of the sample data. So how are you going to figure that out? Well, there's a printout, actually the first printout. We skipped over that earlier. If you go back to the first printout, printout number 1, it's going to give you some descriptive statistics on the different variables. Look at carats, the first one listed, come across. The minimum is 0.19 carat up to 1.03 carats. So there's your range, 0.19 to 1.03. And anything outside that range would give you an unreliable prediction. So we just have to go find the answers and see which one's outside the range. So we'll come back down to that question. That's question number 10. Well, $10,000, that's in the wrong units of measurement. So you say, well, 10,000 is outside the range. Yeah, you're right. But dollars, that's not the right units of measurement. $500, same thing. Now, the last 3 all have carats, but 0.5 carats within the range, 1 carat's within the range, but 2 carats is outside. So the answer being 2 carats, C. Number 11, do you detect any Y outliers, Y suspect outliers, or X outliers in the regression analysis? So obviously there's got to be some printouts that we look at to help us detect outliers. Now, one printout that you're used to looking at for detecting Y outliers is the list of standardized residuals. And if you go back and look at the printouts here, there's no list of standardized residuals. But instead, there is a stem and leaf plot of standardized residuals. And some of you picked up on this on the practice, or not the practice, on the exam 3, where you actually went to this printout and identified what the Y outliers were, because see, standardized residuals kind of makes it easy to figure out what they are without looking down the long list. The stem part is the part like 1 or 2 or 3 standard deviations away. So if you see a 2 or a 3, that's indicating an outlier. So you don't see any at the negative side, but coming down here, there's 2. Okay, so that means, and this leaf of 1 means 2.1. That's the value, 2.1. Oh, that's a suspect outlier. Here's 2 more outliers, 3.2 and 3.4. That's how you read this table, 3.2 and 3.4. Okay, I'll zoom on that a little bit more. 3.2 and 3.4. So there's 2 Y outliers, a 3.2 and a 3.4. There is 1 suspect Y outlier, the 2.1. So 2 Y outliers, 1 suspect by just looking at the standardized residuals, all right? Well, that's the Z-scores. And then how can you find out X outliers? Well, you have to kind of judge it, and you have to go to the graph that plots, I skipped it, sorry, went the wrong way, that plots residuals against X. And look for 1X that's far away from all the others, and you don't see 1X far away from all the others. So no X outliers. No X outliers. And so let's go down and find the right answer. It's answer B. Yep, we got some. 2 Y outliers, 1 suspect Y outlier, and no X outliers. So you had to look at a couple of the different printouts to get that answer. Here's another true-false. Although the assumption of normal errors is not exactly satisfied for this model, the results are valid due to the robustness of the property of regression. Well, let's find a printout that looks at whether or not our residuals are normally distributed. That would be, again, going back to that same stem and leaf plot of the standardized residuals. And yeah, it's not perfectly normal. It's got a little bit of skewness there. But that's okay, right? The property of regression, the robust property of regression, says that it's still going to work well even if you have a little skewness in your data, or even moderate degree of skewness in your data, and that's not too bad. So yeah, that answer is true. That's a true statement. Okay? All right, we'll keep going. Number 13. Which of the following statements about the plot in printout number 7 is true? So we're going to go look at the plot. All right, so printout number 7. And then a little bit later, the next question has to do with printout number 8. So let's look at both printout 7 and 8, and then we'll come back and answer those 2 questions. All right, printout 7, let's see, here's a graph. What are we doing? We're plotting residuals against X. And how did we use this plot? Well, one way to use it is to check for X outliers. We just did that. But another way to use it, remember, is to check that first assumption of the mean error being equal to 0. So you have to know your graphs, which ones correspond to which assumptions. When you plot your residuals against X, it's checking for a misspecified model, which is checking the assumption of mean error equal to 0. And if you see a trend, that means you misspecified the model. Now, remember what model we fit here. This was just a straight line model. We were fitting a straight line model. Do you see a pattern, a trend? I think it's pretty obvious, isn't it? Look at it. Isn't that a curvilinear trend? Yeah, so we're misspecifying the model. We need to add curvature to the model. So let's go back. Oh, by the way, before we go there, printout number 8, that's just a plot of the predicted price against X, and you should see a straight line because that's the model we're fitting. That's a picture of your best model. All right, let's go answer number 13. How about number 7? Well, look at A. The pattern reveals that a curvilinear relationship between price and size may exist. Yeah, that's your right answer, right? Because we just fit a straight line model. We go look at that graph, we see a curve. Hey, we've got to add curvature to the model. Yep. Then the true false on number 14, remember that was looking at printout number 8. The line plotted in printout number 8 represents the line that minimizes the sum of squared errors for the simple linear regression model. Yeah, that's the best fitting line. The line that has a minimum SSE and also has a mean error of 0. Yeah, that's right, that's true. That's the best fitting line. All right, here's another question. Which of the following statements about multicollinearity is true? Now, before we go read the answers, let's go find a printout to help us know what the right answer should be. So we're talking about the multicollinearity issue. Remember that word is a word that represents x's being correlated. X's. So we've got to go find a printout and look at the correlation between the x's. That should be, I think it's printout 3 if I'm not mistaken. Yeah, there it is, printout number 3. There's a correlation matrix. Oh, we're in trouble. Caret is highly correlated with price. Look at that. Wait a minute. Don't get tripped up. Is that a good correlation or a bad correlation? That's a good one. because our dependent variable is price. We want carat to be related to price, but that's not what we're talking about now. We're talking about correlation between the two x's. Remember, we've got carat and color as our two x's. Color being the qualitative, carat being the quantitative. This is the correlation coefficient that's going to be important to look at. Oh, that's really small. We're in good shape there. There's hardly any correlation between our two x's, so our degree of multicollinearity is extremely low. So we got to now we can read the answers, since we know that. This is question number 15. All right. Which of the following statements about multicollinearity is true? Let's read A. The data exhibit very little multicollinearity since there is a low correlation between size and color. Yeah, there you go. That's the right answer. It's exactly what we found when we looked at that printout. So you have to know what's a good correlation and what's a bad one with respect to multicollinearity. All right, number 16, another true or false. If the data exhibit high multicollinearity, they don't here, but if they did, one remedy is to drop one of the highly correlated independent variables from the model. Yeah, that's one way to do it. If you have two very, very highly correlated x's, it's basically saying to you, you don't really need them both. They're essentially the same variable, so just drop one from the model so you don't get confused. So that's a true answer. Now, some more questions about the regression. These pertain to questions 17 through 28. And by the way, the majority of your questions will be on regression because the majority of the time we spent in class was on regression. If you kind of go back and look at how many lectures we spent on ANOVA and how many on chi-square and how many on regression and how many on time series, that's basically the way I'm going to divide up the test. There'll be more questions on material we spent more time on. Okay, it says refer to the same study. Now we're going to improve the model. We're going to consider adding color to the model, the qualitative variable, and that's x2. And then we're also going to add a squared term for carat and an interaction between color and carat and a square term interaction, just like you're doing for your project. So this is really a project question, a series of questions, very similar to your project. Okay, then there's three printouts that analyze models, and they're number 9, 10, and 11. Okay, and the question here, number 17, says, on printouts number 9 and number 10, what is the equation of the complete model? Well, we better look at those printouts. So here's number 9, here's number 10. Oh, these aren't regular regression printouts. These are nested model subset F-test printouts, where you're comparing models, right? And it even says best subset regression models, right? These are printouts that allow you to compare models. And of course, if you're going to compare models, that means one model is a complete model and one model is a reduced model. Of course, the complete model is the bigger of the two. Now, how do you determine the complete model? Let's look at print number 9. All these variables combined together represent the complete model. The forced plus the unforced give you the complete model. So the complete model here has carat x1, color x2, carat squared x1 squared. I'm sorry, that's interaction. Carat by color, that's the interaction term. Then a squared term, another squared term. All right? So the complete model has all those terms. That's like model 1 in your project. And let's go down and look at printout number 10. Again, combine all these together and you get the same model. So the complete model here for both these is model number 1 in your project. And if you go up and look at number 17, you can see that that's answer C. Now, some students pick answer D because they figure, well, model number 1 is the biggest model and answer D has the most terms, so that's got to be the right answer. But wait a minute, look at it. We've got an x2 squared term in there. x2 is a dummy variable. It's a 1 or a 0. That doesn't make any sense. So it can't be D. It's C. C is the right answer. x1, x1 squared, x2, x1, x2 interaction, x1 squared, x2. Okay. All right, now while we're looking at these printouts, let's see what they tell us, and then we'll be able to answer some more questions. Okay, let's look at print number 9. Obviously, it's a subset F-test. It's a partial F-test. So we're testing something about that model. Well, what do you know that you're testing? It's the terms in the unforced row. These are the terms that you're testing. So what's in common with these two terms? Carat squared times color. Oh, curvature, right? That's what's in common. Here we're testing curvature. And remember, you look at the last p-value. So if you look at the last p-value in your test for curvature, is there sufficient evidence of curvature? Yeah, right? HO would be no curvature. HA would be you do have curvature. This p-value indicates very small. Reject HO in favor of HA. You have evidence of curvature. So that's the first thing we learned from printout number 9. Now let's go to printout 10. What are we testing here? Well, again, look at the unforced row. What's in common? Caret by color interaction, caret squared by color interaction. Oh, that's interaction. So we're testing for interaction. And you look at the last p-value and you see a 0.135. There's insufficient evidence to reject HO. Therefore, there's no evidence of interaction. So the first test, there was evidence of curvature, but the second test, there was no evidence or insufficient evidence of interaction. So let's remember that, because we're going to have to answer some questions about it. So now we come down to question number 18, and it's a fill in the blank, just like 19 is. The results shown on printout number 9, that was that first printout, lead us to conclude that there is blank at alpha equal to 0.05. Well, we just said there's evidence of curvature. But curvature relating what to what? Well, curvature in a relationship between a y and a quantitative x. So the right answer is B. There's sufficient evidence of curvature relating price to size. It's not D, because that says insufficient evidence. And you can see some of the other ones have to do with interaction. So it's B. Sufficient evidence of curvature relating price to size. Now, how about number 19? The results shown on print number 10 lead us to conclude what? Well, here we concluded there was insufficient evidence of interaction. That's answer E, insufficient evidence of interaction. Remember, interaction occurs between the two x's. So interaction between color and size. So you have to know your printouts. I can't emphasize that enough. You have to know, where to look on them and so on. All right, so now number 20. Interpret the statement, there is significant interaction between color and size. I asked you that on the second test. I asked you that on the third exam. It's pretty important. It's going to be somewhere on the final exam. How do we interpret that statement? There is significant interaction between color and size. Well, remember, you cannot talk about interaction between two x's without involving the dependent variable, because interaction is in a model, and the model is for a dependent variable. And so we've talked about it a number of times. Interaction occurs when the relationship between y and one of the x's depends on the other. When the relationship between y and one of the x's depends on the other. Okay, so y is price. So the relationship between price and, say, size depends on color. Oh, there it is, answer B. It's answer B. I can tell you on that third exam, here's how most students, I don't want to say most, a lot of students try to answer it like A. Color and size are highly correlated. No, that's not interaction. That's a correlation, but that's not interaction. Okay, number 21. Give the equation of the model analyzed on printout 11. So we've got to go look at printout 11. Here it is. Just a regular regression printout, and look at the predictor variable column. There's your terms in the model. It's got caret in there, that's x1. Has caret squared in there, that's x1 squared. And it has color in there, that's x2. So x1, x1 squared, x2, that's model 3, actually, if you remember your project. So let's go find it. That's answer B. x1, x1 squared, x2. Okay. Another true false, number 22. Based on the results shown on printout 11, the variable color is not a statistically useful predictor of price using alpha equal to 0.05. Well, let's go look at printout 11 again. We're talking about whether color is useful. Color. Well, there's no interactions and so on. All we have is the main effect for color. So the way to determine whether color is a useful variable is go look at the t-test on color. And you can see the p-value is really, really small. So there's sufficient evidence to indicate that color is an important predictor. So if we know color is an important predictor, how do we answer this question? Based on the results of the printout, the variable color is not a useful predictor? Well, that's false. It is a useful predictor. So therefore, the answer is false. Number 23, why do we prefer adjusted r squared to r squared as a measure of the proportion of variance in price explained by the model? Remember, it's going to be important when you have a multiple regression, when you're adding x's to the model, because you can artificially inflate r squared without even knowing it by just adding too many x's to the model. So we use a more conservative estimate of adjusted r squared, so we avoid this artificial inflation. Oh, that's answer C. R squared can be artificially inflated by adding x's to the model. Adjusted r squared cannot be inflated. That's the one we want to use. And that's the one, of course, we've been using any time we look at a multiple regression problem. Number 24. Give an alpha value that will lead you to conclude that the model in printout number 11 is not statistically useful. Not. So let's go look at printout 11, and we got to find the p-value for the model utility. Here's printout 11. Now we're talking about the overall adequacy of the model, and it's this p-value down here. It's the global f-test p-value, so you had to know which one to pick out. The global f-test p-value. We're testing the overall adequacy of the model. 0.012. So now we're trying to find an alpha level that's going to lead us to fail to reject HO. That's going to lead us to say the model is not useful. We don't want an alpha bigger than P. Instead, we want an alpha smaller than P, right? That would be a fail to reject HO. An alpha smaller than P, something like a 0.01 or less than that? Yeah, something like a 0.01. Okay. Well, what do we have for our choices? Oh, there's 0.01, C. So there you had to know, again, your alpha versus P idea. All right, number 25, a 95% prediction over a price. When x1 is 0.5 and x2 is 1 is, and I give you the number. It's not, the printout's not given, but I just tell you what it is. But I say, give a theoretical interpretation of the phrase 95% confident when used with this prediction interval. So what does it mean to say you're 95% confident? You already know I'm going to ask you this. Asked it to you on every exam, I'm going to ask it to you again. Okay, so this is the idea that you have to get this right. Repeated sampling. In other words, more than one interval generated. Theoretically, of course. So in repeated sampling, of all the intervals you could theoretically get, of all those, 95% of them contain the true parameter. In this case, contain the true value of y. Well, that's answer E. About 95% of all similarly constructed intervals contain the true price of a diamond with a size of 0.5 carat and color D. There's your theoretical interpretation of the phrase 95% confident. And number 26, which of the following is not one of the standard regression assumptions about the random error term? Well, the errors are independent, that's an assumption. Mean error of 0 is an assumption. Errors normally distributed is an assumption. Variance of the errors is constant is. But D is not. Variance of the errors is robust, that's not an assumption. And I said there would be one question from Jeopardy Stat, question answer from Jeopardy Stat verbatim on the test. Here's one. Jeopardy Stat answer. The value of R squared in a simple linear regression when price Y and size X1 are uncorrelated. Well, that would mean the correlation coefficient would be 0. And in simple linear regression, the correlation coefficient squared is R squared. And so answer, what is 0? Last question in this series. Which one of the following results would prevent you from recommending the model as a predictor of price? Which of the following results would prevent you from recommending the model as a predictor of price? So we'll just read them all. Would a high value of R squared prevent you from recommending? No, that's a good thing, right? We'd want that to happen. Would a statistically significant global F value prevent you? No, that's good too. I'm going to skip the next one. Would no outliers prevent you? No, that's good. Would no multicollinearity prevent you? No, that's good. But would a very high value of 2s prevent you? Yeah, we might not like that very well. 2s being really high, being really large, meaning large prediction errors. All right, now some other questions pertain to different methods that we covered in class. All right, 29 through 30. For each of the following two studies, select the appropriate method of analyzing data. So here you're going to have to know the key words. All right, so here's 29. Got a group of 18 trainees randomly assigned to one of 3 different home rooms, 6 trainees per room. Each room is identical except for wall color. The 3 colors used were light green, light blue, and red. And a psychologist wants to know, and this is the key, a psychologist wants to know whether room color has an effect on attitude. And if so, here's your key words. She wants to compare the mean attitude scores of the trainees assigned to the 3 room colors. Keywords being compare means. Compare the mean attitude scores. Okay? So this is an ANOVA. Right? That's how we compare means using an ANOVA. The dependent variable, well, the mean of y. Y is the dependent variable. Mean of what? Mean attitude score. So the dependent variable is attitude score. And then the 3 groups, or treatments if you want to call them, right? 3 populations are the color. And so what's the right way to analyze it? Well, there's answer A. Analysis of variance ANOVA on attitude score with a single factor at 3 levels. There's your answer. It's not a confidence interval proportion. It's not forecasting anything. It's not a chi-square test. It's not simple linear regression. All right, number 30. The NHTSA developed a star rating for each new car. Cars with a high star rating are best at protecting the driver and passengers in crashes. And so this group wants to determine, here's the key words, wants to determine whether the star rating, which is measured as high or low, of a new car depends on the weight, which is measured as heavy, medium, or light. Does star rating, high or low, depend on weight, heavy, medium, or light? Well, that's two qualitative variables. Star rating, a high or low value, qualitative. Weight, now weight could be quantitative, but it wasn't measured that way. It was measured as heavy, medium, or light. That's qualitative. Whether one qualitative variable is dependent on the other. Well, that's your categorical data analysis chi-square test for independence. There's your chi-square test for independence. Oh, that's answer D. That's answer D. Some miscellaneous questions. They both have to do with time series. Number 31, true or false? The Durbin-Watson test is used with time series data to test whether the errors from a regression model are correlated. Yeah, that's what a Durbin-Watson test does. Okay? When you have time series data, you want to know whether your errors are correlated, you need to use the Durbin-Watson test to do that. So that's true. And number 32, which of the following forecasting methods takes into account long-term trend, short-term cyclical trend, and seasonal variation, and provides 95% prediction intervals for the forecast? Well, certainly not analysis of variance. That's not any kind of forecasting method at all. And not chi-square test for independence. The only forecasting methods shown there are exponential smoothing, Holt's method, and least squares regression. Well, it's the least squares regression that does the most. Okay, the smoothing ones only do short-term trend stuff. The least squares regression can add long-term trend and seasonal variation, plus give you a confidence interval. So it's the least squares regression. Then, like I said, there were 32 questions where they count, and then there's a 33rd one, but I want you to answer it or you won't get credit for it. But everybody will get credit for no matter what you write down, what you bubble in. And it might not be this particular question, but it's going to be something like this, okay? In terms of, maybe how you study for the test, maybe, how you went and watched lectures, maybe in terms of, whether you looked at your old exams, something like that that's going to help me in terms of teaching the class in the future. So that's a free question. That's 3 points. And so now that's 33 questions, 3 points each. That's 99 points. Well, you get another point just for showing up, okay? So you got 1 free point plus 3 more free points, so there's 4 free points on this final, okay? But don't take it for granted, okay? The final exam, we can get off that now. The final exam is not easy simply because it's cumulative, it's multiple choice, okay? That's why, not because I'm trying to make it hard. And remember this, I'm not trying to trick you, okay? Don't think like that. Don't think, Dr. Singh's trying to trick me. He's trying to trip me up. No, I'm not, okay? So there's going to be a clear right answer on there. Just you've got to use your Spock logic, use your Spock ears, think logical like a Vulcan with all these questions, okay? So I will see everybody, all 650 students at the final exam on Saturday. See you then.